Chapter 3, The Mechanical Advantage, Part 2 of 2. The 6 Simple Machines. A simple machine is a mechanical device that is used to change the direction of the magnitude of a single applied force. They are the inclined plane, the wedge, the lever, the wheel and axle, the pulley, and the screw. No simple machine can be used to decrease a necessary effort force while also increasing the distance that is moved by the load. The inclined plane. The inclined plane is a stationary, flat surface that is set at an angle and is used to bridge two planes that are offset by some vertical distance. The inclined plane is used for moving an object from a lower to a higher elevation that is impractical to traverse directly. A wheelchair ramp is a common application of the inclined plane. The hypotenuse of the right triangle is considered the slope length, s. The slope angle is theta. The ideal mechanical advantage of the inclined plane is calculated by the slope length divided by the vertical height of the incline. The wedge. The wedge is a rigid object with sloping sides that move against or through a load to exert a force. The ideal mechanical advantage of the wedge is the ratio between the slope length and the thickness of the wedge. The ideal mechanical advantage formula is slope length divided by the thickness of the wedge. To find the slope length of a wedge, use the formula slope length equals the square root of the height squared plus 0.5 times the thickness squared. The lever. A rigid bar that is allowed to rotate at some angle about a pivot point called the fulcrum. It is used to move a load when an effort force is applied to the bar. There are three types of levers. A first-class lever, where the fulcrum is in the middle between the load and effort forces. A teeter-totter is a good example. Second-class lever, the fulcrum is closer to the load force than the effort force. An example of a second-class lever is a wheelbarrow. And a third-class lever, where the fulcrum is closer to the effort force than the load force. An example of a third-class lever would be your arm. The ideal mechanical advantage formula for levers is the radius of the effort arm divided by the radius of the load arm. The wheel and axle is a rotating device that consists of a wheel or crank that is attached to a smaller diameter axle. The formula is the radius of the wheel divided by the radius of the axle. A pulley is a free spinning wheel, usually grooved, around which a rope, chain, or belt is passed. The fixed pulley is the simplest form of all pulley systems. The formula is length of the displaced effort cable divided by load displacement, and the ideal mechanical advantage for a pulley is the number of support cables. The screw. A cylinder around which a helical groove or thread is wound. It is used to convert rotary motion into linear motion and is capable of generating extremely large output forces. The pitch. The linear distance traveled in one rotation of a screw. The pitch of a screw must be known in order to calculate the screw's ideal mechanical advantage. The pitch is equal to 1 divided by the number of threads per inch. So the ideal mechanical advantage for the screw is 2 times pi times the radius of the screw divided by the screw pitch. Compound machines. Compound machine is a combination of two or more simple machines that work together to accomplish a task. The ideal mechanical advantage of a compound machine is the product of the ideal mechanical advantage of the simple machines from which it's comprised. For example, the ideal mechanical advantage of a compound machine would be equal to the ideal mechanical advantage of the pulley and the wheel and axle that make it up. Answer the following questions in your engineering notebook. How is mechanical advantage a trade-off between effort and load with respect to force and distance? What is the difference between a machine's actual mechanical advantage and its ideal mechanical advantage, and why is one always smaller than the other? What is the difference between an effort force and a load force? Why might an engineer be more concerned with the power that a machine can generate rather than the amount of work a machine can accomplish? What's the difference between a simple machine's ideal and actual mechanical advantage? And how do mass and weight differ?